The next rule we see in our exploration of derivatives rules is called the chain rule, and this is one of my favorites. It's kind of like the most important rule that we're going to have. So right now, or previously, we've seen the product rule, where we've got the derivative of a product. It's going to be the derivative of the first times the second, plus the derivative of the second times the first when we've got a product. We've got the quotient rule, where if we have something divided by something else, a function divided by another, it is the derivative of the top times the bottom, subtract the derivative of the bottom times the top, all over the bottom squared. Now we have what's going to be known as the chain rule, or sometimes the outside-inside rule. What's going to happen is, if we look at the next function I've given you, f of x equals the square root of x squared plus 1, what we have is a function inside of another function. We've got a composite function here. Now the product rule applies when we have the product multiplication of two functions. The quotient rule applies when we have the quotient division between two functions. Now we've got the composition of two functions, f of g of x. So notation, we can rewrite the above function as the composition. We're going to say f of g of x. So we might see it this fo, that O symbol there means of, composition of f composed with g. Now here, we've got these two functions. F of x, our outer function, is the square root of x. G of x is our inner function, x squared plus 1. That's what we're looking at back top, where we've got f of x equals the square root of x squared plus 1. There is this function inside another, composition. Individually, we can take the derivative of one at a time. What I'm going to do here is I'm going to think about not being g of x equals x or f of x. I'm going to change things instead, making a substitution. I'm going to say that g of x is equal to u. Now, that tells us now that f, rather than being f of g of x, it's f of u. So f of u is going to be the square root of u, where u, our input, is g of x, or x squared plus 1. We can differentiate each individually. F prime of u, well, that's the derivative of the square root. I might think about that as u to the 1/2, and so that would get us 1/2 u to the negative 1/2, which is 1 over 2 square root u. U is going to be g of x, it's x squared plus 1, so g prime of x is going to be 2x plus, just 2x. Using a slightly different notation, what we have here is that we differentiated u with respect to x for g. So that is giving us du dx, because u is g of x, or you are g of x. I don't know. I'm not in English. We've got du dx. Back to the f, you're actually differentiating. I'm saying that is y. That's our function. So we're actually differentiating y with respect to u. U is our variable of differentiation that time. We'll come back to that, where I've got dy du and du dx. Pull that up. What we have is going to be called the chain rule. If g is some differentiable function at x, and f is differentiable at that g of x, the output, then our composite function, f of g of x, which is the same thing as f of g of x, just a different way of writing it, is differentiable. And f prime, the derivative of the composite, is given by this. So what I see is f prime of g of x multiplied by g prime of x. That is the derivative of the outside function, keep the inside the same, multiplied by the derivative of the inside function. Now what we just had, I'm going to look down at my example there, is if we take each one of these individually, saying f of u, where u is g of x, we're coming up with dy du, and u being g of x, we have du dx is g prime of x. So the derivative of our full function, big F of x, is going to be the product of dy du, that, multiplied by du dx. What happens there is, well, dy du dy divided by du times du, it works like our normal arithmetic. We would end up with dy dx. Taking those two, we're going to say dy dx is dy du multiplied by du dx. That's going to give us dy du is 1 over 2 square root of u multiplied by g prime multiplied by 2x. Right now, that gives us 2x over 2 square root u. And you go, 2 square root me? No, 2 square root u. Remember, I said u was equal to g of x was x squared plus 1. Back subbing then, we've got dy dx, which is the derivative of our function, is 2x, I cancel that 2, x over the square root of u. Square root of u is x squared plus 1. There's our derivative. Easy, right? I'm going to take a few other examples. What I think about is it's the derivative of the outside multiplied by the derivative of the inside. Let's take these next two. So the first example, I've got sine of x squared. Now we know that for f of x is sine of x, the derivative is cosine of x. We know that if our function is x squared, our derivative is 2x. So applying the chain rule, I think about this, d dx of f of g of x, it's the derivative of the outside function, so in this case sine of x, keeping the inside the same, multiplied by the derivative of the inside function. So for letter A, y equals sine x squared, dy dx is going to be the derivative of the outside function. Derivative of sine is cosine. I'm keeping the interior the same, multiplied by the derivative of the inside, which is 2x. I'm going to neaten that up in a moment. But notice, derivative of the outside function, keep the inside the same, multiplied by the derivative of the inside function. So here's sometimes why we call this the outside-inside rule, or it's like an onion, where you take the derivative of the outside, then multiply by the derivative of the inside. Now neatening this up, I would write this as 2x cosine x squared. Now notice the difference between that and my second function, y equals sine squared of x. Now you might be thinking, where is the composition there? Well, y equals sine squared of x is the same thing as y equals sine of x, that quantity squared. Now sometimes it helps to rewrite things so we can clearly see what is inside of another. dy dx, our derivative, we're going to take the derivative of the outside function. The outside function is that power to 2. We're going to multiply, applying the power rule, 2 sine of x, subtract 1 from the exponent. I'm just going to write that as a placeholder 1, multiplied by the derivative of the inside function. So the derivative of sine of x is cosine of x. Neatening it up, I've got dy dx is 2 sine of x times cosine of x. This applies for any real number. So we can combine the chain rule with other rules, both the quotient and the power rule, and then later the product rule. Here we've got an example where y equals x cubed minus 1 to the 100th power. Yikes. Using the product rule or the power rule, we might have to multiply that all out. Under the chain rule, there's our outside function. It's raised to the 100th power. That's just a power. Then we've got the interior function, which is our polynomial statement, x cubed minus 1. Taking the derivative, dy dx, I'm going to apply the power rule to the outside function. 100, subtract 1 from the exponent, 99. Notice I'm going to keep the interior function the same, x cubed minus 1. I'm going to multiply now by the derivative of the inside. Derivative of the inside, well, x cubed is 3x squared. Derivative of minus 1 is 0. Neatening things together, we've got dy dx. That's going to be 300 x squared multiplied by x cubed minus 1 to the 99. Derivative of the outside multiplied by the derivative of the inside. Next example. Yikes, there's a crazy quotient rule. I'm going to make this a little bit easier at the start. I can rewrite this as x squared plus x plus 1, all raised to the negative 1/3 exponent. And I see there's our interior function, the polynomial statement, and we have that exterior raised to the negative 1/3. Derivative, chain rule. Derivative of the outside, multiply by the exponent, negative 1/3. Keep the interior the same. Subtract 1, that gives us negative 4/3. So inside we still have x squared plus x plus 1. I'm going to multiply by the derivative of the inside, giving us multiplying by 2x plus 1. Just neatening things up, ordering things around. F prime of x is negative 1/3. I'm going to leave that as 2x plus 1 multiplied by x squared plus x plus 1 to the negative 4/3. And we can rewrite that over the radical, or just call it a day, be done with it. The derivative of the outside multiplied by the derivative of the inside, the chain rule. Here's one with a quotient. All right, we're going to apply the quotient rule on top of this. Now, what I see is there's our exterior function. We have some interior raised to the 9th. So I will apply the power rule. And then when we get to the interior, we're going to apply the quotient rule. G prime of t, derivative of the outside, 9. I'm going to keep the inside, t minus 2 over 2t plus 1. Subtract 1 from the exponent, we have 8. Multiplied by the derivative of the inside, I'm going to apply the quotient rule. The quotient rule, derivative of the top, it's going to be 1, multiplied by the bottom, 2t plus 1. Subtract the derivative of the bottom, 2 multiplied by the top, t minus 2, all over the bottom squared, 2t plus 1 quantity squared. And we can, of course, neaten that up. I'm going to rewrite that as 9. We've got t subtract 2 over 2t plus 1 raised to the 8th. Up top, I've got 2t subtract 2t. I've got 1 add 4. It's going to be 5 for 2t plus 1 quantity squared. We can manipulate, group other terms, but that looks good for now. Oh no, product rule. I don't want to multiply that out. Good, don't. Remember our product rule. So it's a combination of the product with the chain rule. Here's our first function. There's our second function. But within that, we have an interior function. We have these interior functions. So product rule, derivative of the first times the second. We're going to have 5 2x plus 1 raised to the fourth, multiplied by 2, that's the derivative of the first term, multiplied by the second. I've got x cubed, subtract x, add 1 raised to the fourth. Add to that the derivative of the second term, which would be 4x cubed minus x plus 1 raised to the third power. So derivative of the outside multiplied by the derivative of the inside. That's going to be 3x squared subtract 1. So that is the derivative of the second chain rule multiplied by the first. Multiplied by 2x plus 1 to the fifth. We can, of course, group common terms. I see 5 and 2. We would multiply those. 4. Nope, no other constants with the right. There we go. Next up, just going to clear that room. Y equals e to the sine x. There's our function inside of a function. Y equals e raised to the sine of x. Our exterior function is that e raised to the variable, raised to something. Our interior function is the sine of x. So derivative of the outside multiplied by the derivative of the inside. So dy dx. Derivative of the outside stays e to our exponent, the sine of x. Multiplied now by the derivative of the inside. Derivative of sine, we've got cosine of x. Just rewriting that, we've got dy dx is going to be cos x times e to the sine x. That looks fun. That also gets me thinking, what else can we put inside of e? Well, we know derivative of any exponential base is itself. Or exponential base e is itself. What if it's a different base? If I've got some b to the x, namely 2 to the x. I'm going to use a clever substitution. I can write b as e raised to the ln of b. I can do that because exponent base e and log base e are inverses. That is saying e raised to the what number gives us e to the b is b. We can switch that around, convince ourselves with logs. Otherwise, I'm going to use that as a substitution. So d dx of b to the x is the same thing as d to the x of e to the ln of b raised to the x. That is d dx e to the x ln b. Now, applying our derivative rule. E raised to anything is the same thing. So now, we're going to have e to the x ln b multiplied by derivative of the inside. Well, our inside, that interior, make a note, is x ln b. Well, natural log of b is a constant times x. Well, the derivative of that is just ln b because that's the constant slope. So we're going to have e to the x ln b multiplied by ln b. Or, rearranging that, that is e to the ln b to the x multiplied by ln b. Or, all together, since those are inverses, b to the x ln b. So the derivative of any exponential base is equal to that exponential base multiplied by the natural log of the base. Let's see that as an example. We're taking the derivative of 2 to the x. In this case, b is 2. It's going to be 2 to the x multiplied by the natural log of 2. And we can see that that still applies to base e, the same rule. We'd have e to the x multiplied by the natural log of e, and the natural log of e is 1, giving us just e to the x. All right. A couple more. There we go. Next up, yikes, look at that. Ooh, so tangent is our interior function, but that's inside of cosine, which is then inside of sine. So we have a function within a function within a function. Did I get that right? A function within a function within a function. Chain rule. Derivative of the outside multiplied by the derivative of the inside. We'll just do that again, multiplied by the derivative of the inside. Here's our outside-inside rule, where we multiply, and it's like an onion, where we just keep on peeling away the layers. So f prime of x, derivative of the outside. So derivative of sine, we know is cosine. Keep the interior exactly the same. Multiplied by derivative of the interior. So my next function inside is going to be cosine. Derivative of cosine is going to be negative sine. Keep the inside of that the same. Multiplied by the derivative of the inside of that function. Derivative of tangent is secant squared. So we have cosine of tan x multiplied by, I'm going to pull that negative out in front, multiplied by sine of tangent of x multiplied by secant squared of x. That's not too bad. Derivative of the outside times the inside. So you're pulling away one layer at a time by taking the derivative. Last one here, differentiate y equals e to the secant of 3 theta. Now again, we've got a function within a function within a function. We've got e raised to the secant of 3 theta. So there's our function within a function within a function. Our outermost function, dy dx of e, is the same as we started with. So we've got e to the secant, let's spell that backwards, e to the secant of 3 theta multiplied by the derivative of secant. The derivative of secant, we remember, is secant tangent. So we're going to have multiplied by secant 3 theta, keep the interior the same, tangent 3 theta, multiplied by the derivative of the inside of that, which is the derivative of 3 theta. I need to change something. That's not dy dx, that's dy d theta, because our variable of integration was theta. Lastly, multiplied by 3. So e secant 3 theta is the derivative of e. Secant tangent is the derivative of secant. 3 is the derivative of 3 theta. Just rewriting it, I like to put my coefficients, my constants first. We've got 3 secant 3 theta tangent 3 theta multiplied by e to the secant of 3 theta. There you go. Chain rule. Derivative of the outside multiplied by the derivative of the inside. See you in class.